All right, in this unit, we're going to be talking about some different methods of counting, which seems kind of strange if you think about, well, I think I know how to count, but there are some principles that we're going to use when looking at problems that involve looking at how many ways can you count something. Okay, first of all, I want to talk about what's called a sample space. A sample space is basically showing you what some possibilities are. So a sample space lists the possible outcomes. Okay, well, I don't even know what you mean by possible outcomes, you're saying. Well, let's look at this first question. How many boy-girl arrangements are possible in a 3-child family? All right, well, you could have a boy, a girl, and another boy. You could have 2 girls and a boy. There are quite a few possibilities. Those are the possible outcomes. We're going to look at how can we make sure that we show all of the possible outcomes. Okay, another part of this is something called a tree diagram. We can use a tree diagram to show the sample space. So let me show you what that looks like. If you think of 3 children, so first child could be either a boy or a girl. Okay, so we can put like first child here. Then second child. Now, it depends if they had a first child as a boy or a girl first. So take a look here. We could have either a boy or a girl, but if they had the girl first, you could also have a boy and a girl. Okay, and the same thing happens on the third child. If we had the boy, then the boy, now you have another boy, girl, and we could have a boy, girl here. This one will be boy or a girl, and this one would be boy or girl. And so this gives us a couple of scenarios. So let's try to list the sample space now. So the first possibility is that we could have a boy, boy, and a boy. Okay? Then looking at the next possibility, maybe we had boy, boy, girl. All right, and then what if we went boy, girl first, and then boy, girl, boy? Boy, girl, boy, and then we also have boy, girl, girl. All right, going down to if we had a first child as a girl, then you would have girl, boy, boy, girl, boy, girl, 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 boy, and girl, girl, girl. That is the sample space right there. Okay, it's a list of all the possible outcomes. And the strategy we used to get the sample space was to use a tree diagram. Okay, so let's try a few more questions like that. So Hannah plays soccer. The soccer uniform has 3 different sweaters, red, white, and black, and 3 different shorts. How many different variations of uniform can the coach choose? Well, let's look at, I guess we'll call them the top and the bottom. What could Hannah wear for the top? She could have a red sweater, a white sweater, or a black sweater. And then for the shorts, or the bottom, maybe if you don't like top and bottom, if you want to put sweater and short. Okay, if she puts on the red sweater, what could she have for short? Well, it could be red, white, or black. If she puts on the white sweater, what could she have? Red, white, or black. And if she puts on the black sweater, again, she could have red, white, or black. Okay? So it says how many different variations of the uniform could there be? Let's list the sample space. We could have red, red. We could have red, white. We could have red, black. We could have white, red. Now, is that the same as this? It's not, because one's short and one's a sweater. Okay, we could have white, white. We could have white, black. We could have black, red, black, white, black, black. There is your sample space. So the question asks how many different variations? There are 9 variations. Okay, so that's using the tree diagram. We could also use a chart, right? So these are, let's say these are the short colors, and these are the sweater colors. So, you know, if we chose this spot here, this would mean we would have red, red, or red black or red white, etc. Okay, white red, and we could fill this out. And again, you're going to see there are 9 possibilities. Okay. Well, this leads us to what's called the fundamental counting principle. Okay, rather than write out the sample space every time, rather than use a tree diagram, there's kind of a bit of a shortcut here. Okay, you saw we had 9 variations. Well, notice that for the first option there were 3 options, and the second option there were 3. This is basically 3 times 3. Okay, if we go back here, we had 2 choices here, 2 choices here, 2 choices here. What's 2 times 2 times 2? It's 8. Alright, this is called the fundamental counting principle. It says that if the event can be done in L ways, and the event 2 can be done in M ways, and the event 3 can be done in N ways, then we can go L times M times N to find out the total number of ways. So for the above example, uniforms and sweaters, we could go 3 times 3, so there would be 9 possibilities. This is very useful. Let's look at this next question. A luggage lock opens with correct 3-digit code. So 3 digits. Think of 3 numbers. Each wheel rotates through the digits 0 to 9. Now, if we list all of those possibilities, there's actually 10 digits. Okay? So how many digits could you put in the first spot? Well, all 10 of those, right? You could have any one of those. Okay, what about the next spot? Again, all 10 of them. And in the next spot, any of those 10 digits would work. So if we go 10 times 10 times 10, there are 1,000 possible codes. Now, I don't know about you, but I would not want to do a tree diagram with 1,000 different possibilities. Okay, it's much easier just to consider each of the 3 digits and what can be filled in for each of those digits. Okay, let's see if we understand that question. In that case, we were allowing repetition. I could use the same digit over and over again. Suppose that you can only use each digit once. Okay, repetition is not allowed. So what are my choices for the first digit? It's still 10. I could have any of the numbers 0 to 9 in that spot. Okay, now I go to the next spot. I have used one of the digits in here. I don't know which one of them, but it's one of them. So how many choices do I have for the next spot? Does it make sense that it would only be 9 because I've already used one? And what would be in the last spot? Now I only have 8 choices. Okay, so now there's only 720 possible codes if I don't allow repetition. In other words, I wouldn't allow a number like 111. Okay, each number would have to be different. Okay, let's keep going here. So how many 4-digit numbers? Okay, so 4 digits. Okay, pen stopped working. See if you can figure this out while I'm fixing my pen. How many 4-digit numbers can be written? If the digits can be repeated. Okay, so how many are there here? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 possibilities for the first number, and 9 for the second, and 9 for the third, and 9 for the fourth. So what is 9 times 9 times 9 times 9? 9 to the power of 4. This is 6,561. Okay, now how many 4-digit numbers can be written if the digits cannot be repeated? Okay, we've seen one like this, so I can still have 9 digits for the first one, and then it's going to be 8, and then 7, and then 6. Okay, what is that? Quite a few less, 3,024. Okay, how many even? Okay, got another problem here. Now the number has to end even. So for example, if my code was 1358, this would be okay. But 1357, this would not be okay because that's an odd number. And that makes this whole thing odd. Okay, so when I'm thinking of my 4-digit number, if I want it to be even, I need to put an even number here. I need to put either a 2, 4, 6, or 8 there. So I only have 4 choices in that location. Okay, so that's a little bit of a clue. So always deal with conditions first. I'm going to put always do conditions first. So this one says it has to be even, so deal with that first before you do anything else. Okay, so now you've used one of the numbers. So these are my choices. And let's say I used the number 4. Let's say I use that to make it even. It doesn't have to be 4. You know, let's say we use 2. It's the same question. How many digits are left to use for this spot? Well, now there are 8 for that spot because I've used one up already. I don't know which one, but I know it's one of these 4. Okay, and then if I use one more digit, say it's a 5, then I have 7 left here and then 6 left here. Okay, so 8 times 7 times 6 times 5. This is 1,680. All right, another one. A computer store sells 6 different computers, 4 different monitors, 5 different printers, 3 different multimedia packages. How many different computer packages are available? Well, there are 4 things to consider. First of all, there are 6 computers. And then we have 4 monitors, so I can combine those with 4 different monitors. And then I have 5 different printers. Okay, and then 3 different multimedia packages. Okay, so think about that. If you pick a computer, a monitor, and a printer, and you change the multimedia packages, you've changed the whole deal. That's why we multiply them all together. Okay, so I think that's 360. All right, in Manitoba, how many potential license plates exist using all 6 characters? Okay, we're assuming that these are not custom plates, right? We're assuming that in Manitoba, the first 3 are letters, right? And the next 3 are numbers. Okay. So how many different letters are there? 26, right? So I could have 26 different ones in that spot, 26 different letters there, 26 different letters there. And then how many digits are there? How many numbers? Well, if you go 0 to 9, there are 10. So this is going to be times 10 times 10 times 10. Okay. So quite a few here. We get 46,656,000. That's how many possible license plates exist. That doesn't include the ones where you can put what you want on it, the custom ones. Okay. A few more examples. How many ways can the digits 1, 2, 3, 4, 5 be arranged? Okay, so 5 digits. Oh, sorry, that's 1, 2, 3, 5, 6. How many of those 5 digits could go in the first spot? Any of the 5. Okay, so then we've used one. Let's say we used the 1. How many can go in the next spot? 4, and then 3, and then 2, and then we only have one number left there. Okay, so 120 different ways. If we did the same question, but we allowed you to use the number over and over again, then you would have 5 times 5 times 5 times 5, because you could use any number in any of those spots. Okay, I think that's 3,125. Okay, a few more. Well, this is an interesting one. How many ways can first, second, and third place be arranged in a race of 8 runners? So we're only worried about first, second, and third. If you've ever been to the horse races, they call this the Trifecta. Now we're assuming something. We're assuming that any of the runners could win. Okay, let's be honest. If we took 8 people and had a race, everybody knows that some have a better chance of winning than others. Like if I was in the race, I'm pretty sure I'm not going to win. But we're assuming that anyone could win. So of the 8 runners, who could be in first place? Well, let's assume all of them. So if one runner wins, how many could finish second? 7. And then how many could finish third? Again, this is the fundamental counting principle that allows us to figure out how many possible ways things can occur without actually writing them all out. Okay? How many 5-digit even numbers can be arranged? 5 digits. So it has to be even, so we have to do this first. And you could only use the numbers 2 or 4 here. So 2 numbers. Okay, now if I use one of those, how many is left for here? Well, now there are 4 numbers left, and then 3, and then 2, and then we use the last one. Okay, does that make sense? We have to start here by putting an even number so that the whole thing is even. Okay, and then we just use up what's left after that. So that's 48. Okay. How many 4-digit even numbers can be made using the digits? Oh man, this is a hard one. Put a star by this. Okay, 4-digit. What goes here? A 0, 2, or a 8. 0, 2, or a 8. So there's 3 possibilities here, right? Yeah, sort of. Okay, I want you to think about this for a second. Let me give you 2 possible scenarios. What if I decide to put the 0 here? How many choices do I have for this spot then? Well, I would have 2, 5, 7, 8, or 9. There would be 5 choices for that spot. Okay, but what if I use the 2 here? How many choices do I have for this? Well, I can't use the 2 then. Can I use the 0? Can I start a number with 0? No, you cannot. So this is a problem. Okay, we can't do this just with one simple case like this. What you have to do is consider 2 cases. Case 1 or case 2. Case 1, we're going to use 0 here. So we're going to use that 0, that's our one choice. This is going to allow us to use any of the other 5 numbers here, and then 4 numbers, and then 3 numbers. Okay, and so that's going to be 60 ways. Well, now let's consider using the 2 or the 8. So there's 2 possibilities. If you use either the 2 or the 8, let's just say we use the 2. How many choices do I have for this first spot? Well, I only have 4 because I can't use 0. Okay? And then to make it even tougher, okay, let's say I use the 5. How many choices do I have for the next spot? Again, it's 4 because now I can use a 0. So the 0 is okay here. And then there's 3 numbers. Okay, so that's going to be 24 times 4 is 96. So 156 ways. Okay, that's a tricky one. For sure, that's tricky. Okay, let me just see how much further. We can do this a little bit here. Disjoint, 2 or more sets having no elements in common. Remember that? Mutually exclusive, 2 or more events that cannot occur at the same time. So let's keep that in mind when I look at this. Count the number of possibilities of drawing a single card and getting either a black face card or an ace. Okay, well, how many black faces are there here? Well, those are all of these cards. Oh, black face card. Black face card is just these ones right here. So there are 6. And then we also want to know how many aces are there. There are 4. Okay, so how many possibilities? 10 possibilities. Okay, why is that the case? Because face cards and aces are disjoint sets. Okay, but look at this next one. Either a red card or a 10. Well, how many red cards are there? There are 26. And how many 10s are there? Okay, 10s are right here. Do you see how the 10s overlap though? So I'm going to say 4, but I'm subtracting 2. What's this 2? This is the overlap. Okay, so here I have red cards. Here I have 10s. But here we have the 10 of hearts and the 10 of diamonds. They overlap. Okay, so there would be 28 possibilities here. So we need to keep this in mind when we're doing some of the counting. All right, we'll stop there. And here's your homework for this lesson, page 235. All right, make sure you do that and check your answers.